equations, please. Just an equation, all right? Induction. 1 hand, 2, 1.5, 3, 2.5. Okay. Divide and conquer. So like you're okay. Backtracking. Okay, that's interesting. Now this one I'm not going to see any hands, right? Dynamic programming. Not a single hand. Okay, that's sad. But okay, so we're going through each topic. I'll make sure to be a little interactive, so don't be shy. Any answer is correct. You know, I'd rather fail in the review than fail in the exam, so don't be too scared to give the wrong answer. And yeah, we'll just go speed through it. So, from my mic. Okay.
I should have been holding this. Okay. Well, let's get started with recurrence relations. So, the thing about recurrence relations, they're just an equation. Don't get scared by them. Don't freak out. It's literally just a way to represent the runtime of an algorithm, right? So on the left, you're going to see a function, and the function represents the function of your algorithm, right? And then on the right-hand side, it's just explaining the runtime of the algorithm. Okay, so it's just a powerful tool for analyzing recursive algorithms, right? Because you see T of n on the left and T of n on the right. Now, who can tell me what this one at the bottom, or tell me 3 things about this recurrence at the bottom? Or does anyone recognize it?
It's O of n log n.
How do you know that?
I just memorized it.
Okay. Great for an interview, maybe not great for, or maybe great for exam, maybe not great for interview. Okay, well, Sammy.
So the O of n, this is like the merge sort algorithm. The O of n
Close.
is like the linear.
Yeah. Okay. So this. Yes. Okay. Yeah. Good. So Sammy. So Sammy's identified it as a divide and conquer algorithm. He said on the right hand side the ON. He said that was like the merging of merge sort, right? So then, what do you think the left hand would be? Dividing, right? So divide and conquer, divide and combining. The better word to use here for this O of n is combining, right? Now, you were right by saying merge sort, but also you're technically not right, because recurrence relations only represent the runtime. It's not that merge sort has one or it's not that this recurrence can only represent merge sort. It could represent another algorithm that has the same runtime as merge sort, but it's not just exclusively merge sort. And the same goes for binary search. You can represent it with a recurrence, with a different one, but it's not exclusive, if that makes sense. Any questions on that? Can we see how it's merge sort? Because there's 2, to the 2 in front of the n, because on merge sort you go on the left half and the right half. And then this n over 2 is called the subproblems, right? So you're halving the array, you're given n elements, and then you half it, you recurse 2 sides, and then you combine it in the last step. And then if you were to solve it, you'll see n log n, right? So, when you get your exam, you're going to have a list of recurrences, and then you're going to have to solve them, right? For me, this is the easiest way, the DC recurrence theorem, right? This is made by Gopal, or Dr. Panaragan. And honestly, just memorize these 3 at the bottom. Obviously, memorize the form of whenever you see recurrence with T of n equals AT of n over b plus f of n, then you know you can use the DC recurrence theorem, right? And then what it says is, we have a that's greater than or equal to 1, or a b that's greater than 1, they're constants. You can suppose that there's a constant c in the form of a of f over n, or a of f over, a f of n over b, right? Equals c f n, okay? This equation is important to memorize. In fact, when you get your exam, I want you to write this equation here, and then you're going to write the 3, how you say it, the 3 rules here, right? And I'm going to show some examples, and we're just going to speed through it, because really this portion is really just about memorizing the theorem. Now there's another theorem, which I'll show later, and if this one doesn't vibe with you, you can use the other one. But this part of the exam should really take, I don't know, 10 minutes maximum, hopefully not that much, right? So next slide. So you may get a question like this, and you had it on your homework, where you had these recurrences, and a lot of you would be more inclined to draw it out as a tree, but what if you got this? Are you really going to sit down and draw 6 branches? I hope not. You know, I don't know if you're Picasso or something, you could draw that many lines, but I'm not doing that. So you would just use the formula that you had. So in this case, if you get a recurrence like this, what would your A be? 6, right? And then your B? 3. Okay, now you have the form A f of n over B equals C f of n. So what do you think C would be? You'd put 6 in the place of that A. Now you have f of n. Now we can just write, instead of f of n, we could just write in terms of n. So you would just have like A of n over what your B was, which here is 3. And then you would have C of n, right? So if you do that, also, is everyone following along? Is any questions before I show the answer? No questions? All right. So if you do that, you'll get 2 because you have 6 f of n over 3. Cancel out the f of n. And then it's just 6 over 3. So C is 2. 2 is greater than 1, which means if you go back to your rules on the slide ahead, C is greater than 1, so then you'll see n is base n and log b of a. And really all it is just writing down the rules and memorizing. The first thing on your exam, just write them down and then you'll go back when you're flipping the pages, okay? All right, so next one. What's your A? 1. What's your B?
2. Okay, so it's going to be 2 f of n over b equals c f of n. But what's n?
In this case, is a little tricky.
But it's right in front of your face.
Was it 1?
1. Is it Billy who said that? Right. It's 1. So on this side, you're just going to have c times 1, and then it would be like 2 of 1 over, oh, sorry, no, it's 1 times 1 over 2, if I'm not mistaken. Which will yield 1. I could be wrong here, actually. I wonder if that's verified. Okay, that one might be awkward. Maybe C is equal to 1, maybe it's not. You guys fact check me. Maybe this one slipped through. Anyways, it's as simple as putting 1 here instead of n, and then just do the math. I have to fact check myself. I hope that's not wrong. That doesn't look right. C might be 2 here. But we're going to speed through. Recurrences aren't that big of a deal. All right. Next one, where you have n squared instead of 1. So what happens to n here? You see? N is now squared. So then you have to square this inside here, where it's n over 3. Now it's going to end up being like 2 times n over 9 equals c n squared. But you have to write it in the terms of your n. So if you're given a squared n, you have to make sure that this function on the right is your n squared. Because remember, f of n is really just this bit at the end. It's the combination step. Yep, and?
So is f a constant?
F is a function. N is like, I'm not going to make the wrong statement here, but just f is a function. N is what's the terms of your function. That's as much as I can say.
If it's the same function on both sides, you can essentially cancel it out.
Exactly. So write it in terms of what's up there. So like if they give you a +1, it's in terms of 1. If they give you a plus n, it's in terms of n. Whatever they, sometimes it might even be a cubed, but that I've only seen on a homework, I think. So it's as simple as writing out the rules and then trying to get your math down. Right? Oh, sorry, there was a question? Sorry,
Is
Billy.
A supposed to be 2 or is it
2. Oh, what you mean, the squaring?
6? The A equals and B equals 3.
Oh, sorry, it should be 2. That's a typo. These ones are made quick. My bad. All right, yeah, that should be 2 there. All right. Okay. Now there's Master's theorem, which is the alternative. Really, I don't really care for it that much. There's an Abdul-Bari video for it. If you like this one, you can use it. And don't worry too much about trying to get like pictures, because I'll send you guys the slides. You'll have it, and also I'll send you the revised slides with 100% like correct answers. So yeah, again, recurrences, just memorize the theorem and use it. And then here you can see an example where you use Master's theorem on a crazy recurrence, and it gave you big theta of n squared, right? Hopefully this portion won't be that serious. Just make sure you pick a theorem, only practice with that theorem, and then memorize it and write it on your exam, right? So now, sorry, question, Sally?
So, on the exam, does Blue let us pick whatever theorem we want, or is there a specific one that we have to use?
That might be a Caitlin question, who's sitting at the back conveniently, but I don't want to bother her. She doesn't know. Well, okay, when I took Blue, you could use whatever. Typically, when you take Hall or Go Paul, they really want you to use DC recurrence theorem. You might be safer using DC recurrence theorem, but a case in the argument can be made for using Masters. It should be okay. Any more questions? Cool. So let's get to the more important stuff, which are proofs. Because yeah, you can get 40 points on a recurrence section like me, but you can write a really dumb mistake and lose like 35 points like me. So let's make sure we get proofs down. We got Santiago here to go over this section, and yeah.
Alrighty. Okay, so mathematical induction. Essentially, a mathematical induction, it's a proof where we try to prove that any given mathematical statement is true for any natural n. You might be thinking, why is induction really important for an Algos class? Well, we're going to be using it for proof of correctness. Yeah, next slide. So, mathematical induction comes with 3 steps. The first one is the base case or the termination condition. You guys might be familiar with this terminology from your recursive function. So essentially, what a base case is, it's the smallest possible natural number n where our mathematical statement is true. So it could be 1, 2, 3, so on and so forth, as long as it's the smallest one. Now, a little bit warning though, is if we actually find a small natural number n that's true, but then the next value, say n plus 1, makes the statement false, then we need to find another base case, because that would mean that our proof is false. So essentially, like an example, let's say that 1 is our base case, but then 2 doesn't work, then we need to find another base case. Just work for it. Now, we have our second step, inductive hypothesis. So this one is what is going to help us with our third step, which is going to be the meat of our student. So inductive hypothesis is where we're going to assume our statement holds true for an arbitrary number k. So what does that mean? Well, we're going to have an example to show that. But it will help us with step number 3, inductive step, where we're going to show that our mathematical statement is true for k plus 1. All right, so now we're going to look at the different types of induction. We have 2. So we have weak induction. Now, weak induction is when we assume that our hypothesis is true for an arbitrary natural k. But wait, didn't we already talk about mathematical induction is that? Well, it's actually pretty different. See, weak induction refers to when we prove that it's true for a singular natural number k. Okay? A singular natural number k. How does that look like? So, I'm pretty sure you guys have seen this proof before, if you guys have taken discrete math before. But essentially, the example is, prove that the sum of the first n positive integers is given by the formula 1 plus 2 plus 3, so on and so forth, plus n equals n times n plus 1 divided by 2. Now, what this means essentially is that our base case will be 1. Now this makes sense, right? Let's plug in 1. 1 times 1 plus 1, that's 2, divided by 2 equals 1. Okay, so we write. Okay, so we write that as our base case. Now, number 2, what is our inductive hypothesis? Well, it's given right there in the problem. Our inductive hypothesis is that the sum of the first n positive integers equals n times n plus 1 divided by 2. Okay? So now that we have our inductive hypothesis, we can go ahead and do step number 3, which is inductive step, which is where we try to find a statement for n plus 1. So what we do is we replace this with n plus 1, then n plus 1, and n plus 1. So we replace n plus 1 for all n's. And then we're going to use our inductive hypothesis, which was that n equals n, well, equals this formula, right? And then if we do the math, you guys can do the math, but once you do the math, you'll see that it will equal to n plus 1 like this. And if you want, I can show you the math like after the review session is over. But yeah, strong induction. All right, now strong induction. So strong induction is where we're going to assume that our statement, that our hypothesis is true for all natural number up until an arbitrary number k. So that's why it's strong, because it's going to be true for that series up until k, meaning that starting from our base case is true all the way to our k, and then after that we're just going to show that it's true for k plus 1. Now this is a very simple one. Prove that 2 to the power of n is less than n factorial. We're going to see that our base case would be, let's see, it would be 2, right? Because 2 to the power 2 is 4, and then 2 factorial is just 2. And then our inductive hypothesis will be that 2 to the power of n is less than n factorial. Then our inductive step will be to show that this statement holds true for 2 to the power of n plus 1 is less than n plus 1 factorial. And then once you do the math, it will hold true. This one is a little bit funky because you got to do a calculation which I call a logic heap. Which is, you use the base case to your advantage, which is very weird. Which, again, I'll be more than happy to show you how this one goes after the review session. But yeah, for now we'll continue. All right, so before I start on proof of correctness, you might be wondering what is best to use, weak or strong induction? Now, I'm just going to tell you, it doesn't matter which one you choose, because both of them are logically equivalent. So it doesn't really matter. I'm pretty sure that most of you are going to use strong induction anyway, so yeah. So now that we talked about mathematical induction, before I move on, does anyone have any questions about mathematical induction before I talk about proof of correctness? No? Yep.
Why would we prefer to use strong or weak induction?
Strong or weak induction? Well, you're going to use it to show that it's true for all arbitrary number k, and once I explain what proof of correctness is, you're going to see that you would prefer it over it. But yeah, you'll see it. All right, so writing a proof of correctness. So proof of correctness, it's a method of which we verify that our algorithm will output the correct, will input or output the correct thing for all possible inputs. And how do we do that? Well, we do that by mathematical induction. So here's an example. Proof of max element of an array. So the question is asking us, assume that we are given an array S of n elements, return the max value of S. And here we have the pseudocode. Does anyone want to tackle what this pseudocode does really quickly? If we have any volunteers? Go ahead and digest that before we move on. Yep.
I mean, it looks like it finds the max of the left-hand side, finds the max of the right-hand side, and then compares the values.
Exactly. It's simple as that. And it's a recursive function as well, right? So, and like I said, it returns the max value of S. So proof of correctness is you're going to need to have a good knowledge, a good grasp of what your algorithm does before you tackle it. So I suggest try to look at the pseudocode if they give you the pseudocode, or if you're writing the pseudocode. Try to understand how your algorithm works before tackling the proof of correctness, right? So what is our first step for mathematical induction? Base case, right? So what is our base case? So here we can clearly see that it's trivial that our base case is when our length of the array is 1. Why? Because it would just simply output the max, right? It has nothing to compare. So trivially, that would be the max. Okay? So now we have our inductive hypothesis. So how do we write inductive hypothesis for proof of correctness? Well, we say that we're going to assume that our algorithm is correct for every set of sizes less than n, right? And then we're going to do our inductive step. So our inductive step will show us that using the induction hypothesis, we can confirm that it is correct for any inputs less than n, right? By induction, max 1, right, and max 2 are the correct maximum values of the sets S from A through M and S from M plus 1 to B, right? And then from there, we can conclude that max 1 and max 2 must be the maximum of n minus 1 plus 1, which is just simply n. And that's it. And honestly, proof of correctness is really simple. You guys don't overcomplicate yourself with proof of correctness. Essentially.
I have one thing.
Yeah.
Say this to my.
Oh, one thing to add on to what Santiago just said there. Keep it simple, right? You know, there's like the software design theory of keep it simple, stupid. Same thing applies to proofs. Don't get into the weeds of syntax and semantics. Don't try to avoid buzzwords, right? You can see how the proof here clearly describes the algorithm in plain English without saying anything too crazy, right? When you write the base case out, keep it a short sentence. When we know it's one, we're done. When you want to explain and communicate your inductive hypothesis, first word of the sentence, assume, right? Assume, and then you can finish it up. So any questions to that?
Any questions about how we tackled proof of correctness?
Hello. I hope y'all aren't tired because this is like our halfway point. So now I'm going to go over divide and conquer. So here we have an example problem of find the median of two sorted arrays. So given two sorted arrays A and B of different lengths or the same length, describe an algorithm to find the median element in the union of A and B in O of log n time.
You guys should recognize this one, I'm sure. Hopefully, unless you have a zero at this point.
Hopefully not.
So, anyone want to tackle it?
Any guesses? Throw something out there. Never know.
Maybe a base case.
Yes.
Sam.
I mean, one thing for sure is since it's O of log n, it's a divide and conquer, more specifically like a binary search algorithm.
Okay. Why did you say that? So everyone else
Why?
can know?
Oh, because of the time complexity. I mean, I'm just
Yeah,
looking straight up
exactly.
at the time complexity and the log, like really, stood out.
Well, I mean, the obvious base case is if the length of the string or the array is 1, it's going to be
Right.
Yes.
Right. Can we think of another base case too? More than just one element.
I heard you.
I heard, Billy, did you see two?
having 2 elements.
Two. Why two?
Because you just got to compare 1.
Exactly. So, ready for the next slide?
All right. So, like you said, best way to find it is through using the search method. And so, basically, the easiest way to understand this problem is to obviously know how the median works. And so, you're going to start off by finding the medians of array A and array B. And let's say array A, the median of array A is the greater median of the two. Okay. So, with the greater median value, values that are greater than that, because, failed to mention this, the two arrays are sorted. So you already know, once you find the median of array A, all the values greater than that can't be the median. They're too big. So what you can do is divide the array in half and keep the values from 0 to MA, to the median of A. And then if for MB, it's the smaller of the median, and so you're going to start off with MB and then all the way to the end. And then if M of A is smaller, you're going to do the opposite. You're going to keep the larger of the values of M of A and then the smaller values of M of B.
ask them if they want to do a proof? Anyone feeling brave enough to try to?
You should be able to do the base case. We kind of already talked about it. Anybody want to try the inductive hypothesis and the inductive step for this one? Obviously, it's going to start off with assume.
What do we assume?
What are we assuming?
You're assuming if it holds true for the base case, and that's hold true for k plus 1, k plus 1 values in the array.
Almost there.
Almost.
Almost there.
Almost. Right direction.
That's like you kind of mixed the inductive hypothesis and the inductive step.
Yeah, it's like you skipped it. Yeah.
But they must hold true for arbitrary value.
Yeah.
Maybe we'll show it to them.
All right. So you have our base case. If it's just an array of one element, it's just going to output the one element. And then obviously, so we're going to, you can notice that our inductive hypothesis starts with assume. And it's assuming that it's going to work for everything for an arbitrary number of n that's going to be less than k. All of your proof of correctness are basically going to have the same format. You're just going to be mixing out the values and everything. And so it's critical to understand that our algorithm works for all values of n less than k. And so when we move on to our inductive step, we're going to assume that we're at a value of n equals to k. So obviously with our inductive hypothesis, we don't know if it works or not. And so we're going to look at one case where the median of array A is less than median of array B. So, okay, we find our elements, and we know when we work through the algorithm for this, is that if m of A is less than m of B, you need the greater elements of the smaller median array, and then the larger element, the smaller elements, the median of array A, and the larger elements of the median of array B. All right, and so as you can see through our thing, we're literally dividing the array in half. And so because of these arrays are going to have a smaller length than what they originally had, which is k, and over n divided by 2 is going to be less than k. By our inductive hypothesis, this is just going to work. And so our algorithm works by inductive hypothesis.
We have one question from Yusuf over there.
So is it saying that each subarray is number 2 length, so both subarrays together is length of n, and we've already proved that the algorithm works for length of n?
Yep.
Therefore it's true?
Yep.
Yes. It's a matter of subproblem size. Your subproblem size here is n over 2, because you're dividing in half.
Yeah.
So, any other questions? Did your answer on the homework look something like this?
I hope it did. And if not, that's okay.
Cool. So we can go to the next question, which should be new to you guys. Or sorry, we'll do pseudocode first. Don't forget pseudocode in your exam. Sorry.
Here's your pseudocode. We have the base cases of its element of an array of 2 elements, and then we have our recursions, or else if median of A is greater than, or if median of A is less than. And so over here, obviously start off with a race case where they both equal each other, and then we have our recursive case where it's the two elements, and so you just got to compare them. And then we have our recurrence, and as you can see, we're doing it in O of log n because we're literally dividing the array in half, and then it's just +1 for the arithmetic. Any questions?
Any questions for Lynn? Right.
This was an example when Sammy said that he saw the recurrence on the first slide and said it was merge sort. This is an example of the same thing, but with the recurrence for binary search. Can you see? This here is a recurrence that is for quote-unquote binary search, but we can clearly see that there's an algorithm that is not binary search with the same recurrence. So you can see that our recurrence can represent multiple algorithms. So I'll hand it back to Lynn.
Y'all are ready? We can move on to the next problem. This one's a lot easier to understand, in my opinion. Little simple. This is Hamming weight. So if you don't know Hamming weight, it's the number of ones in the binary representation of n. Does anybody remember how to convert a number into binary from 2425?